welcome back to Arxflix. Today, we're diving into a groundbreaking paper titled Neural Discrete Representation Learning. This research introduces a novel generative model, the Vector Quantized Variational Autoencoder, or VQV. Let's break down its unique contributions and insights. Learning useful representations without supervision remains a major challenge in machine learning. VQV addresses this by learning discrete representations rather than continuous ones. This helps in avoiding a common issue known as posterior collapse. VQV essentially combines the variational autoencoder framework with vector quantization. This allows for discrete latent representations, which are more compatible with modalities like language and speech. Here's an illustration of the VQV model. It showcases how the encoder output is discretized into embeddings before being fed to the decoder. The model has an encoder, a prior, and a decoder. The prior is learned, not static. The encoder output is passed through what's called a discretization bottleneck. This maps the latents to one of the k embedding vectors in the space. The posterior distribution is categorical, calculated by a nearest neighbor lookup. The embeddings are taken as inputs to the decoder, completing the forward computation pipeline. The model uses a combination of reconstruction loss, VQ objective with L to error, and a commitment loss to train the encoder and decoder. This combination ensures that the embeddings and the encoder outputs remain stable and effective. The paper explores various domains to highlight the effectiveness of VQV. Let's look at some results from different applications like images, audio, and video. The left shows original ImageNet images, and the right shows reconstructions from a 32 by 32 by latent space. Despite reducing dimensionality drastically, the reconstructions are only slightly blurrier. Here are samples generated by a pixelkin prior trained on the VQV latents. The quality is impressive given the discrete latent space. VQV is also effective in unsupervised learning of phonemes from raw audio. Left is the original waveform, while the middle and right show reconstructions and speaker conversion, respectively. For video, the model generates sequences conditioned on actions. This has significant potential for applications in reinforcement learning and robotics. The top row is conditioned on the action move forward, while the bottom row is on move right. The generated frames maintain visual consistency and correct local geometry. VQV introduces a robust and flexible method for learning discrete latent representations. It performs well across various domains, from images to raw audio, demonstrating the versatility and potential of discrete latent spaces. This concludes our overview of neural discrete representation learning. If you found this video useful, don't forget to like and subscribe for more deep dives into research papers. Until next time, keep learning and stay curious. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.